welcome to the Android Services Black Magic talk. I wasn't responsible for the title. Let me just give you a brief idea as to what we're going to talk about. Specifically, this talk is geared for those of you that are interested in understanding how Android works underneath the hood. So yes, if you're Android developers, you can, for the most part, ignore a large section of this because you just tend to consume the APIs and things hopefully tend to work rather than not work. But if you want to know how they work, what's under the hood, and how are these services put together, essentially this is the talk for you. My name is Alexander Garganta. I'm actually local, live actually close to San Francisco. I moved out of San Francisco recently. I work for a company called Maracana. We provide training on open source technologies, Android in particular. I deliver classes on Android, write courseware on Android, mostly internals, security, that sort of stuff. I also happen to run the San Francisco Android user group, also Java one and a couple other ones. But that's kind of how I get my pulse on the Android community, and by coming to conferences like these and talking to you guys. So that's about me. Let's get started. And by the way, for those of you that are just walking late, I do want to reiterate that we'll be recording, or I'm recording this entire talk, and we'll be posting the video from this on our site, and I'll show you again the URL at the end. So let's just see by show of hands, how many of you have never seen a diagram like this prior to coming to this conference? Oh yeah, 1, 2, 3. Okay, awesome. So most of you have. And this is not about this diagram. It's not about how the layers, are put together. It's more about, understanding what happens when, for example, an application like a browser wants to talk to, grab your location, ends up talking to some sort of a call, ends up talking to some sort of a driver. How does that flow work? How are these services put together? So it's really more about this part of the stack, but with an idea that we want to understand the total flow through the Android stack to understand essentially how do these services essentially give us, or implement the APIs we want to use as developers. So let's get into this. But before we do, I actually added this slide recently on the Android startup. I think it's going to help explain some of the things we'll see later. I'm assuming that most of you have some idea as to how Android boots up, but let me just go over this quickly. When you first turn on an Android device, what typically happens is your CPU executes some hardwired boot ROM code, which tends to load this first stage bootloader, which tends to find then the second stage bootloader, which then loads or mounts your boot partition, finds the kernel, loads the kernel, initializes the kernel, or asks the kernel to initialize itself by passing it some parameters, and so on and so on. The kernel does its thing, and then the kernel goes and initializes some drivers, like the binder driver, which we'll see later on, and then executes this init. I don't know why this got cut off. The init program, which is basically the very first user space executable. This init, in turn, essentially goes and launches a whole bunch of daemons, or daemons, as some of us like to call them. Like, for example, UFND, Service Manager, Voldy, netd, installed, and so on and so on. And later on, it gets to this zygote process. Zygote is basically the first Dalvik, or I should say Android runtime, or the Dalvik virtual machine process that runs, which then forks itself and starts this system server. System server goes and executes some Java class called system server, interestingly enough, loads a whole bunch of JNI libraries, as you will see, and then goes and loads a whole host of services, like the Activity Manager service, Package Manager service, Power Manager service, Wi-Fi Manager service, and so on and so on and so on. So our goal here is to understand essentially this part of this picture. There are other services that are not necessarily built in Java, and they're not even part of the system server, like, for example, the Surface Flinger, the audio flinger, I guess I should say, media player service, camera service, and so on and so on. They also are part of the services. They are just not inside of the system server. So with that said, please go ahead.
Did Zygote start media server too or not?
No. And media server started from init. Zygote forks itself to start the system server. It used to be that system server was responsible for starting some of the things like camera, and so on, Surface Flinger, but that's no longer inside of system server. So all of this, by the way, assumes ice cream sandwich, and some of the lower levels assume my particular phone, the Galaxy Nexus, which assume most of you have. Well, a large portion of you have. Any other questions? Cool. So let's take a look at some of the services. And so the goal here is not to go and dissect every service because we don't have the time, nor do I actually know how every single service on Android works. I've only been looking at this for years, but I haven't really gone into everything. But the goal is to understand how they are similar in terms of how they're put together, and also how they're different. And we'll start off with a simple service. And in fact, you'll see that most of the rest of these diagrams or the slide deck will be just diagrams like these, with a bunch of boxes and a bunch of lines, pointing from these boxes, or between the boxes, I should say. And my job is to take you through essentially this flow, from say an application that wants to consume a service to then how the service actually does its job. So we're going to start with the vibrator because I find that's one of the simpler services in terms of how it's put together. Yet it kind of has this full stack. So it goes all the way from an application that can use it down to a kernel driver that can actually do something and interact with some sort of a device. So for example, vibrator. Say you had an example activity that wants to vibrate the device for some sort of haptic feedbacks. And you want to now initiate that vibration. The way you do this is you end up using something called a vibrator. It's essentially right here. You instantiate it, literally, just do a new on it. Not all services are used this way. This one, you essentially directly grab a vibrator. Now, what happens when you actually say, hey, vibrator, I want to vibrate the device? Well, before you can even do that, something else needs to happen. Okay, so we need to backtrack a little bit. When Android booted, just to remind you, going back over here, Zygote started a system server. Well, one of the things the system server did, which is now over here, is that this system server Java class instantiated a vibrator service, essentially as another Java class, which binds to some JNI shared libraries, which we'll get to later on. But that's not important just yet. That vibrator service, it basically ends up being, it extends from something called iVibratorService.stub. Where does this come from? What does this do? Well, the communication between Android applications and these services, for the most part, happens through this IPC framework in Android. It's called Binder. So just to backtrack a little bit more, coming back over here, most of the bridging from this part of the stack to this part of the stack is through IPC, and most of that is implemented through Binder. Binder is basically not a custom, but we should say a custom, essentially IPC framework for Android, but it doesn't come from Android. It's actually something that used to exist back in the BOS days, some of you remember BOS. We also see that the jump from here to here, essentially from the application framework to native layer, happens for the most part through JNI, which essentially is the Java native interface that enables a Dalvik virtual machine to load shared libraries written in C and C++, and then bind to the functions implemented by those, and essentially map Java methods onto these C++ functions and execute them at runtime. And then most of the essentially conversion, if you will, or jump from the native layer or the user space to kernel happens through system calls, a lot of which is implemented through simple ioctls or simple IO writes, reads, and so on to the drivers. So let's go back to the vibrator. So when the system server basically loaded this vibrator service, well, that vibrator service basically extended from this stub. This stub is part of this iVibrator service interface. This interface is implemented in a language called AIDL, stands for Android Interface Definition Language, which is part of Binder. And it describes the capabilities of the service to the outside world, namely you guys, the clients of this service, assuming you are developers. And now we'll see what role that plays. What's interesting is that this vibrator service, even though it's a service, needs to be somehow discovered at runtime. And now we have to go and talk about this thing, the service manager. What is the purpose of this? The service manager is one of these daemons that gets started early on, which is right here, by init. And its job is to essentially serve as a naming service for these services that you actually wish to use. And so what happens is the service manager goes to this kernel driver called binder and registers with this driver as what's known as a context manager. And there can only be one context manager. And so the idea is that if anyone wants to get a context manager from this point forward, all they need to do is go to the binder driver and say, hey, who's your context manager? And they get essentially a pseudo pointer back at the service manager. So let's go back again to this diagram. Whoops, sorry, vibrator. So system server builds the vibrator service. Then what it does, it goes to the binder and says, hey, binder, where is your service manager? It discovers that the service manager is right here because service manager pre-registered. Then the system server goes and says, hey, service manager, how about you remember where the vibrator service is? And essentially what happens is that now after this call, there's a pseudo pointer back to the vibrator service from the service manager. Okay? And how does this pseudo pointer is remembered under this name vibrator. It's literally just a string, text. So let's go back to our client. Okay, so now our client finally wants to vibrate the device. Well, what it does when it builds the vibrator is essentially, as you will see, nothing more than a little proxy. Vibrator actually goes, first and foremost, before the vibration happens, over to binder and says, hey, binder, where's the service manager? It gets it the same way the system server did. Then the vibrator goes, after it does that, it goes to the service manager and says, hey, service manager, I need the vibrate service or vibrator service. And essentially at that point the service manager gives it, remember how the service manager had essentially this pseudo pointer? Well, that pointer is now delivered back to the vibrator, and now you can think of the vibrator as knowing where this vibrator service is. So they discover each other, or the client, if you will, discovers the service at runtime. Now, this discovery is usually cached. This information is cached, so it's not like you're repeatedly doing this over and over again. Okay? Okay, so now we have the service we want to talk to. So what happens next? Now you say, okay, go and vibrate. The vibration actually, or the request to vibrate, doesn't happen directly through this because we can't. You know, this lives in a different process altogether. We can't talk to it. This is where the binder comes into play. Binder is that IPC, or inter-process communication framework. So what happens is that the vibrator actually goes to this proxy. From proxy goes to the binder driver. The binder driver executes via something called libbinder and another binder thread through this stub a method on the vibrator service to actually request the vibration. So what is the role of the proxy in a stub? Well, the vibrator or the binder driver, which is over here, is actually very simple in terms of it doesn't know anything about these rich Java or C++ objects you'd like to pass as requests from, say, a client to a service. It just knows about simple, essentially, bytes, if you will. In fact, it talks in terms of these so-called parcels, but that's even beside the point. So the purpose of the proxy and the stub, so specifically these two components, this proxy, and whoops, sorry, it's kind of hard to draw when the laptop is at an angle, and this stub is to facilitate the marshalling of data from the Java layer down into something that the binder can understand, and from binder back into the, essentially think of it as the Java layer. There's of course more than to it that happens behind the scenes, but that's pretty much all we need to understand at this time. Okay? So without a proxy in the stub, we would essentially have to talk to the driver directly using ioctls, and when I say driver, I mean binder, and that would be way too low level for our liking, right? So essentially, we as developers never really see this proxy in a stub, but when we are talking to this vibrator, we are inherently using it in order to get to the service. So let's assume now we got to the service. Okay, so now this request came from the vibrator via this stub into this vibrator service, right? So it got here from this activity back into the binder and then over this way. What happens? Well, this request actually runs inside of a system server on a thread called a binder thread. So binder, one of the things it does, it maintains a pool of threads that are used to essentially service these requests. And so one of those threads is fetched, and now that thread essentially is responsible for driving that request. So what happens then? A vibrator, in the case of vibrator specifically, what it does, it goes and essentially packages that request into a local object that it calls vibration, I believe, and it then passes it into a separate thread, a vibration thread that it internally manages. And it then returns the request back to the client. So at that point, the client is no longer waiting for that request to complete. Think of it as an asynchronous request. Or you set a request and then you forget about it. You don't have to worry about it. Right? From that point forward, the vibration is supposed to happen from the vibration service. So this vibrator service executes now its local thread, which is essentially package your request, which says how long should we vibrate this device, or what sort of pattern should we employ to vibrate this device. And at that point, the vibration service wants to execute the request. So how does it do it? It actually doesn't talk to the driver directly. Instead, it jumps into this C code, or C++ code, basically that is the JNI layer, and that is inside of something called Android server's shared library. The purpose of this is really nothing more than to wrap something called HAL, the hardware abstraction layer. So what is the purpose of HAL? Well, different devices may have different, essentially, vibration capabilities, so different hardware, right? Some may have actuators, some may have some specific motor, some may have other sorts of ways of vibrating, or they may not at all support vibration. So because this can differ, different manufacturers will presumably provide different ways of initiating vibration. They will presumably also have different, essentially, kernel drivers that know how to do the vibration. And so in order for Android porting to be as easy as possible, Android essentially creates this abstraction of the vibration device, and that is the hardware abstraction layer. And this hardware abstraction layer essentially lives in the user space. So I know the drivers themselves are essentially or make up another hardware abstraction layer, but that's in the kernel. And so this in the case of Galaxy Nexus, for example, this vibrator C is already provided by Android out of the box. And what it tends to do, it literally opens up this kernel driver, or the handle to the kernel driver, and writes to the kernel driver, doing a simple I/O write, the number of milliseconds for which to vibrate the device. In the driver, what happens is the driver, now in the kernel, goes and grabs a wake lock. Well, first of all, locks, its internal mutex, grabs a wake lock, and then changes the pin on a GPIO essentially device, which then triggers some motor or actuator or something to actually go and do the vibration. At that point, later on, essentially that expires, the wake lock is released, and essentially the vibration stops. The interesting thing about the vibration service is that it can actually implement the pattern, right? So it's not just about a single vibration. What if you want to vibrate for a little bit, then stop, then vibrate again, and then stop, and so on and so on. So that state as to what to execute next, what is my next vibration, actually lives inside of the vibration service. The vibrator service CPP is extremely simple. It actually just serves as a bridge. It doesn't have any logic inside of it. The vibrator.c is, again, also in this case fairly simple. The HAL tends to be in this case very simple. It just essentially causes the driver to implement the next vibration. And then this driver knows how to talk to the actual hardware. Okay? So does this make sense? Because this is essentially, we went into a little more detail on this one, but and it gives you hopefully an idea as to how these services work. Any questions so far? Sorry, this stuff? Yeah. So these are additional shared libraries. This is basically like Android runtime is something that essentially powers the Dalvik and so on and so on. The lib binder is what facilitates the communication with binder, and there are other sort of like libc and whatnot. Those are just additional shared libraries that are part of this process. They play a role, but not a key role in understanding how this works. Let me just actually make sure to explain the different components, what the responsibilities of different components is, and then I'll come back to your question. So again, the purpose of this, the purpose of the vibrator is to essentially hide from the client, you guys, the fact that you're even using binder, this IPC framework, because that tends to be not complicated, but involves a little bit of additional error handling, lookups and whatnot. You're just using a simple Java object. To you, it looks like a POJO, but essentially does a lot of work underneath the hood. The purpose of the proxy is to convert the Java request into a binder request. The purpose of Service Manager is to facilitate the lookup and the registration of services. The purpose of binder is to facilitate the essentially calling one process calling another process through through this kernel driver. So that is the heart of the IPC mechanism in Android. The purpose of the stub is to take the binder request and convert it back into a rich Java request. The purpose of the system server is to initiate and start our services and register them with the Service Manager. The purpose of the vibrator service is to actually implement a number of things. One is add a little bit of extra logic, like implement a pattern. It also, by the way, does security checks. It checks whether the client is permitted to do the vibration. I'll come back to how that works. The purpose of this is really just to bridge from Java, or Dalvik, I guess, into C. The purpose of the HAL is to essentially bridge from the, bridge into the kernel driver using a standard API. The reason why, again, we have HAL is because we want to allow the manufacturers to essentially implement alternative, or provide alternative implementations of this. And finally, the driver knows how to talk to the hardware. Now you had a question.
Yeah, so from system server side, is that a message queue-based implementation, or does it work with the thread?
So is it, I didn't hear it.
The messages, are they queued on the server, or is it working on the thread pool?
There's a thread pool inside of a system server on which the different requests are being serviced. So no, they're not queued. Now, individual services, one of the interesting things they do, for example, the vibrator service, it actually goes and locks the vibrator device to avoid concurrent vibration from multiple clients. So that will essentially behave like a queue, but in terms of being able to use different services concurrently, no. The threads are essentially provided from the binder pool.
Following up on the units of IPC, is that the portion of shared memory, or how does that actually work?
In terms of the IPC, the actual parameters are copied from process to process. In terms, if you have large, sections of data that you want to avoid copying, then you could use something like ashmem, which is essentially request a shared memory region, then pass to the other process the file descriptor to that region, and now you can share memory. Okay? So let me just mention one thing about security, which is actually the other real reason why we have these services, right? In the case of a vibrator service, what it does, it goes and checks for whether the client has the Android permission vibrate. How does it know that? Well, what's interesting is when this client, this example application, submits the request through binder into this, right, and down here, whether it likes it or not, it goes and passes its identity into the system server. How does it do that? Essentially, binder, in addition to the call that it submits, it passes the UID of the calling process. And in Android, because every application runs under unique user identity in a separate process, that's a separate point, and essentially that unique user identity can be translated back into which application that belongs to. And then from that, we can go to the package manager service and say, hey, which actual permissions has this application been granted by the user at install time? And then we simply check for whether our permission, the one we want to enforce, is on the list. Now, all of this sounds complicated, and there's, Android does this essentially in a single line, single API call, single method execution, where you simply say enforce calling or self-permission, or check for whether the caller has the permission. And essentially, this is what happens. We get the UID, convert it into the application, from application, we figure out which permissions it has, and we simply check whether our permission is on that list. Okay? So let's take a look at some of the other ones. You'll now hopefully see that there's a lot of this is, the pattern is fairly similar. So for example, power management. If you want to grab a wake lock, I'm assuming most of you have some idea as to what wake locks are. It's Android's way of essentially helping applications control or influence the way power is managed in the device. So essentially whether the device will stay awake or not. So say you wanted to write a music playing application, you wanted to grab a wake lock so that when the device, essentially the music continues playing even though the screen may power off or normally the device would want to go to sleep. So what you would do is you talk to the power manager. Power manager would actually go talk to the service manager and ask for a power service. This power service comes from here, and it was again created by system server and put into or registered with the service manager on startup. So when you then go, now that happens, Power Manager, when we use the Power Manager to say in wake lock, we actually get a wake lock object, and internally that wake lock object retains the reference to the actual service. So when we say acquire the wake lock, that is when we initiate the call via this proxy into the binder through the stub into the Power Manager service. Power Manager service then maps that wake lock request into its own internal representation of the wake locks and essentially multiplexes these wake locks for multiple applications. And then, assuming that there isn't one, Power Manager service will then go and talk to something called Power. Power has a bunch of JNI methods which are implemented here by this shared library, Android runtime. And from there, Power goes and jumps into HAL, right? HAL, or hardware abstraction layer, for power. From there, we simply, again, by the default, we go to this kernel driver and we ask for a wake lock. That's when we're actually talking to the wake lock driver. And then, of course, the call continues back the other way, and we that returns, and we now know, okay, so we have a wake lock. The release pretty much works the same way. Now, it just so happens that, like I said, Power Manager service actually multiplexes multiple wake lock user space or application requests for wake locks into essentially its own internal, single wake lock that it holds for the kernel. And the reason for that is so that if an application were to die or so on, so that it can basically go and have that application's wake lock, pseudo wake lock, be automatically released. But that's essentially how at least the interaction with the Power Manager for the wake locks works. Any questions? Okay, alarms. I usually like to say this is how I got here this morning. This is what happened this morning when I was sleeping and I wasn't really feeling like coming here, but unfortunately, my alarm thought otherwise. So I basically, even last night, I set this desk clock application on my phone to request an alarm. How does that work? Again, internally, you can look at the source code for this. That talks to this alarm, or I was interacting with this alarm clock activity, which talks to something called alarms, which internally uses a context implementation. Now, what is this context implementation? Many of you who have actually written Android applications, you've probably at some point used that method called get system service. Right? That method exists on the context interface. It's actually provided by this context implementation. That's what your activity extends from, for example, or services and whatnot. A lot of them extend from this context implementation. Now, what the context implementation does in the case of a lot of services, it will go and look up these remote objects, i.e. these, in this case, alarm manager services, and it will then go and store a reference to that object into its own internal cache. So by the time you go and say, give me the alarm manager service, this might have already been looked up. Right? So you're not actually causing that to happen. That might have happened as soon as your activity was, for example, first constructed. It doesn't happen like this for all services, but a large number of services are preemptively fetched and essentially already there. So by the time you need to use them, the cost of getting that service is almost negligible. So it's essentially a map lookup. So then what happens, you're given essentially an alarm manager. And again, this is the part of the confusion. When I started looking at Android, I was confused as to why do we have services and managers, right? Why do I get a manager even though I'm asking for a service? So hopefully you're realizing the services are what exists on the side of the system server, right? Services do the actual work. The managers are really nothing more than clients to your services that hide all this complexity of binder and in some cases threading from you. So anyway, the alarm manager service wants to request an alarm, right? So what it does, it creates a pending intent in this case. It basically goes and, actually this application creates a pending intent, goes to the alarm manager services, hey, I want to, here's this pending intent that you're going to execute in the future to call me back. Then the pending intent gets captured in this little parcel through this proxy via the binder back into the stub. We're now on the other side of the, I guess, in another process. The stub is extended by the alarm manager service, and now the alarm manager service gets the request to schedule this next, essentially, callback. Now, what happens next is that the alarm manager service then internally maintains a list of these pending intents and when they're supposed to fire, whether they're exact, inexact, whether they're repeating, and so on and so on. But let's assume that it needs to schedule a wake up. What it then does, it talks or loads or initiates a local call to set the alarm via this, JNI, essentially a class or file, if you will. It's not really a class, even though it's implemented in C++. And what that does, it directly talks to the alarm driver. In this case, there is no HAL because there's an expectation that pretty much all Android devices are going to implement the alarm in the same way because the alarm driver is directly provided by the AOSP or the Android source tree. It's not something that OEMs are expected to essentially get too creative with. Now, some people ask me, why do I use alarms? Why don't I just use local timers or something like that? Why do I go through the trouble of using an alarm just to schedule a callback? Well, the purpose of the alarms is that this is the way we get to wake up, right? So if the device is sleeping, right, it's in a suspense state. If you have some runnable code or a timer that you set up yourself in your application you want to fire, that's not going to fire if the device is already sleeping. You need something to wake up the device. Well, that something could be an incoming packet coming in over, I don't know, some connection over, like, say, C2DM or some sort of push notification into your device. But what if that doesn't happen? So then your device may never wake up, and you're going to miss coming to this great conference. So instead, this alarm driver talks to the internal RTC, essentially, or the real-time clock in the SoC or the chip that we're on, and schedules it to raise an interrupt sometimes in the future based on what is the next thing that we need to wake up. And so what then happens is that this alarm manager service, this guy, goes and has an internal thread that literally just waits, blocks on this alarm to fire. This alarm then essentially just waits for the interrupt to fire. So RTC fires the interrupt, wakes up the alarm driver, if you will. Alarm driver unblocks and essentially returns to the alarm manager service thread. That thread now says, oh, what should I execute at this time, of the day? And then it looks at an internal list of things that essentially need to run, finds your pending intent in there. It converts that into a real intent, and that fires back and calls your application, and now your application does its thing. Okay? Does this make sense? Okay. So that's alarms. Package manager. So let's say you wanted to install a new application, and let's assume that your application is, let's say, on the SD card. So you're kind of installing it via like a local, one of those file managers, or maybe you're installing it by downloading it from a browser, right? So not Market, that's what I'm trying to say, or Play Store. So what happens is that you would use something called a package manager, package installer APK. This is one of the system applications that ships with Android. So that fires in response to you raising an intent to essentially install this APK. And what that does, it calls this package installer activity. Package installer activity calls this install app progress, which then goes and gets a reference to a package manager. How? We simply say context.get package manager. If you look at the source code for that, again, what it does, it literally goes over here. This actually gets the application package manager. That goes to the system or to the service manager, says, hey, who is registered under this package name? Service manager knows about that because way back at the boot time, system server took this package manager service and registered it with the service manager. So now the service manager answers that question. So let's say you now want to proceed with installation. So again, what happens is this activity or this install progress talks to the application package manager via this. That talks via proxy to the binder, from the binder into the stub, from the stub into the package manager service. But here's a problem. Assuming you accept your permissions and whatnot, by the way, all the permission checks would have been done way back when, but assuming you now want to actually commence with installation, the issue is that, remember how I said every app runs with its own unique identity? Well, for that to work, the directory that app has and into which it will be installed needs to be owned by that same user, right? So, but what is the problem? The problem is the system server runs as the system user, doesn't run as root. So it doesn't have privileges to go and create this directory structure and change its ownership to this newly created, essentially, user ID for this application you're about to install. It doesn't have that capability. So what does it do? Well, on Android, we essentially go and have a separate daemon called install_d that does run as root and does have that capability to essentially create a directory structure for this new about to be installed application. And so what happens is that this package manager service literally sends a request via this installer down into this install_d. And how does it send this request? It sends it as a Unix socket message. So this is yet another IPC call, but now we're not using binder, we're using Unix sockets. This install_d socket is being read by this install_d daemon. This install_d daemon gets that message, parses it, says, okay, this is what we need to do, fine, and it goes and essentially executes those commands or creates that directory structure and changes the ownership. Now, why didn't they just simply do all of this in system server? Again, if they wanted to, they would have had to run the system server as root, but running it as root would have meant that, it'd be extremely easy to find some of the, a way of essentially compromising an Android device and exploiting, some sort of a weakness and essentially gaining root. Basically, the system server is way too big. Its surface area is way too large, and so there would be many different ways of essentially trying to exploit it. So they wanted to isolate the privileged operation into a separate daemon so that they minimize the risks of somebody essentially gaining root. Okay? That's essentially how your installation happens. And by the way, even if you're doing market-based installation, the left side will be different, but the right side, i.e. what the market or the Play application does, pretty much is exactly the same. Please. It could. So certain install_d could use binder. In this case, binder is basically assumes that the services are written as objects. So it essentially assumes a more object-oriented infrastructure. Install_d is extremely simple. It's written in C for the most part, if I remember correctly. And you will see that in a lot of cases, when it comes to communicating to those daemons, a lot of the communication actually happens through Unix sockets rather than binder. There wouldn't be nothing wrong for them to use binder, but in a lot of cases, the Unix sockets are kind of more simpler for this purpose, for what they're trying to accomplish. Let's talk about Wi-Fi. So here, I'm not talking about how the actual Wi-Fi itself works, meaning how do the packets go from your application down into the Wi-Fi hardware. That essentially is the responsibility of the Wi-Fi driver that plugs directly into the kernel. And when we initiate a call to say, your server.com, basically that routing and all of the flow of data happens through the kernel. There's no involvement from the point of view of the rest of the Android framework. Yes, there's involvement from the setting up the routes and whatnot, but we don't really get into the business of sending packets via, say, sockets or via binder. That'd be extremely inefficient. So instead, this is really about Wi-Fi management. How do you control Wi-Fi? How do you initiate a scan? How do you enable Wi-Fi, disable, change to Wi-Fi direct, that sort of stuff. So let's say you had an application, like this example application, again, that wants to do this. Inside of this example activity, the first thing you would do is you would grab a system service called Wi-Fi Manager, right? Wi-Fi Manager, as soon as you would get it, would essentially, like we said before, go to the binder, then the service manager. From the service manager, it will learn that there is in fact a Wi-Fi service that had been registered with the service manager by the system server upon startup. So this part, you can see, it's pretty much consistent. We didn't even have to talk about this part. You're hopefully seeing this, how the initial registration happens. Now what happens is, again, we go to this proxy, from the proxy into the binder. From the binder, we execute an onTransact method on the stub. From the stub, well, the stub is extended by the service. Okay, they're actually one and the same object at runtime. But you can kind of think of them as the flow goes this way. Now the service runs. But here's the thing. Wi-Fi is fairly complicated, meaning that the Wi-Fi hardware can be in many different states. And so what we need is a way of replicating those states that exist in the hardware in essentially a model that we maintain in the software, so we know what to tell our users to what, essentially what is the state of the Wi-Fi hardware. And so what Android does is then essentially uses some sort of a Wi-Fi state machine which maintains that model essentially in memory. Okay, so it replicates the state of the hardware at any given time. And the reason why we need that is, the actual driver and the rest of the Wi-Fi stack may in fact be unloaded, as we will see in a moment. Now, when you say you want to initiate a connection to some hotspot, the Wi-Fi state machine then initiates a call to the Wi-Fi native. Wi-Fi native is really just a bridge to the Wi-Fi CPP, which is essentially just the JNI bridge to the Wi-Fi hull. So just like we had for power and vibrator, we now have the Wi-Fi hull. Wi-Fi hull is, in fact, does different things on different phones. Like, for example, on a Galaxy Nexus, it directly communicates to this something else. You'll see something called the WPA supplicant. On a Nexus S, for example, one of the things it does, if your Wi-Fi is not even on, it will first load the Wi-Fi driver as a kernel module to insmod before it proceeds to try to talk to that kernel driver. Okay? So depending on the device, your driver may in fact be loaded at all times, or it may be loaded and unloaded on demand by this hull. So what happens next? Well, the actual communication with the driver is fairly complicated. And so Android did not want to re-implement the wheel, especially because there is already something in the Linux community that we use in a lot of Unix distributions called WPA supplicant, which is responsible not only for the WPA authentication, but also the communication with the Wi-Fi hardware, assuming that this Wi-Fi hardware implements, or the driver for the Wi-Fi hardware implements this NL802.11 framework, driver framework, if you will. So essentially what happens is that this Wi-Fi hull talks to this WPA client, which wants to use the WPA supplicant to do the actual configuration. But the problem is the WPA supplicant is actually a GPL piece of software. And we don't want to link to GPL because of all the licensing issues with that. Once you link to GPL, then your code needs to be GPL and so on and so on. Instead, what we do is we don't talk to it directly. We actually send a message to the WPA supplicant via yet another socket. And so then the WPA supplicant gets the message and then communicates with the actual driver. Okay? So this part is fairly standard. I mean, the part of this communication is fairly standard because both of these tend to come from the Linux, standard Linux community, if you will. But the top of the stack, of course, is what's unique to Android. Does this make sense? Okay. So location. I actually talked briefly about this yesterday during the keynote. I don't know if any of you remember it, but let's just recap some of the key points here. Location service. So let's say you wanted to write an application that knows or gets the current state of the device or the current location of the device. What do? Again, you get a system service and you say, give me a system service called location. And what you get is the location manager. Location manager, again, just like we already know, goes to service manager, grabs a reference to this location manager service. So when you now say, okay, I want to get the last known location, again, so this part is, you'll see it's fairly consistent, goes via this proxy, down into the binder, back into the stub, and down into this location manager service. The location manager service, depending on the provider you want to use, say you want to use GPS, will fetch the correct provider, assuming you have GPS, say the GPS location provider, which actually doesn't do much work other than bridge to the C code, which is essentially the JNI wrapper. That JNI wrapper also doesn't do a lot of work, except that it bridges to a special HAL, hardware abstraction layer, for GPS. Right? Again, why do we need these things? Well, because there is no such thing as a standard way to write GPS drivers. Right? Most GPS drivers are some sort of serial ports, but different GPS drivers may be implemented by different manufacturers differently. And so we don't want that. We want a standard way of communicating to these things. And so the only way for that to work is to provide a level of abstraction. That is the purpose of HAL. So this GPS driver, where it comes from depends on the device. So on a Galaxy Nexus, because it's based on OMAP, 4460, it'll come from this particular shared library. What's interesting is that the HAL can be licensed under any terms. And on most of your hardware, most of your Android devices, the one thing that tends to be closed sourced is this hardware abstraction layer. That's the one thing you don't have. That's the one thing that's actually making it hard for you to take standard, Android AOSP3 compile it, and just dump it onto your device. You can get 99% of it there, except for the hardware abstraction layer, which needs to come from your manufacturer and be compatible for that particular version of Android. Okay? So anyway, in the case of this HAL, I don't actually know what it does because it is closed sourced even on Galaxy Nexus. But what I do know is that it happens to talk to some sort of a serial device, which is over here. And then that talks to some sort of a GPS chip, which obviously gets your data from the satellites. So now, like I said earlier during my keynote, and I wanted to go a little bit more detail, oftentimes people ask, well, why do we have so much complexity? Why so much, so many layers of indirection, so many layers of abstraction? Doesn't that add a lot of overhead, latency, wastes memory, and so on and so on? That's true. But for example, let's take a look at how this helps you as a developer, right? You could potentially try as a developer, say, to talk to the driver itself. But if you did that, you'd have to know how to talk to proprietary, essentially, driver. And at the same time, you'd have to have that code somehow available to you, which a lot of the OEMs don't want to give it to you because a lot of their secret sauce is in that code. They actually would prefer you not to have access to it. Okay? And also, most of the time, you don't want to code your application so you're specifically just asking for GPS. You want to ask for find location, or you want to ask for different sources of location, right? You don't want to actually communicate to a GPS driver. So that tells you right off the bat that one of the things that this location manager service does, it enables you to essentially aggregate data from different sources of information, or location information, right? So that's what it does. So now, what is the purpose of this location manager? Why don't we just go to directly talk to this location manager service? Why do we need this location manager? Well, remember how, hopefully some of you at least here have used the location manager service and have actually written applications that use this. One thing you probably would have done is you would have registered a listener with this location service, which is actually a manager, to receive updates from the sensor when a new GPS data becomes available. How does that actually work? The way that actually is implemented is that this location manager service implements a thread that it will wait for these updates to come from the driver via, like again, go over this way, then go this way, then go this way, then go this way, right? And it actually holds that state. So it waits for that data to become available. What it then does, when the data does become available, it'll actually want to send that data back to you, right? Because you asked for it. But you all along, you weren't waiting for it. You weren't wasting your UI thread waiting for this data to come back to you. Nevertheless, the data does come back to you. Well, if the data were to come back directly to you, right, to execute directly your callback, the problem is that that execution would happen on a binder thread. And now, what you would have had to do in your application, you would have to take that data, that piece of location data, and essentially pass it via some sort of a handler onto a UI thread if you wanted that data to be somehow mapped onto the UI, say to update some sort of a UI, like act on it in the context of the UI. And that would complicate quite a bit the model, right, the API model that you want to work with. You don't want to know what handlers are for the most part. Of course, there are reasons why you should, but in this case, you probably don't want to. Instead, you would just expect that the callback will happen on the same thread that is from where it is safe to update the UI. And as we know in Android, you cannot update the UI from a non-UI thread. And so instead, what happens is this callback actually comes back into a listener inside of the location manager, which acts as a bridge to actually call into your listener that you provided, say, from your activity. And so by the time the data comes back to you, it went through the binder into this first stage listener, then onto the handler, passed as a message to your listener, and then your callback got fired. So the purpose again of these managers, right, in a lot of cases, is to provide that ease of use API that essentially shield you from all this knowledge of threading and the knowledge of IPC that you'd otherwise have to worry about. The purpose of the service, in the case specifically of the location manager service, it enforces security checks as to who can access the location. It aggregates sources of information. It provides these location updates, right? So you don't have to even run, because you can actually fire those updates via these pending intents. So your application doesn't even have to waste memory running, waiting for it, if you don't want it. and essentially can go and provide the, or the threads needed to go to the driver and wait for the data to become available. So there's quite a bit of, value add in these different layers along the way that seem like they're just, adding latency and wasting memory, but they actually, do contribute to the overall, execution model. Any questions so far? Okay. Let's talk about the audio policy. You can see kind of how there's more lines here, and the next slide, I just gave up on lines because there's just too many things, but bear with me with this one. Let's say you wanted to, play some audio, or you wanted to, control the audio playback on the device. Android actually tries to abstract these two things as two separate concerns. One is I want to, essentially play audio or play video, whatever. The other is I want to essentially request a focus with which I'm going to play back this audio, or I want to change the volume of the device, or I want to change the ringtone, or I want to change some audio policy of the device. So in this case, we're just going to look at the audio policy, not the actual audio playback. So let's say you wanted to, I don't know, mute the device. What happens is, again, your application is going from this example activity to the audio manager, which grabs a audio service from the service manager, and then via the proxy, again, this part is the same, via the proxy, via this binder, talks to this stub. From the stub, it goes to this audio service. But here's the thing. Most of the actual audio control and the state of the audio system is not in the system server. Here we see a completely different daemon running called the media server. That's where audio and the audio flinger and whatnot live. So what happens is this audio service actually talks to something called audio system, which actually just talks to this audio system CPP. That's essentially the JNI call, which talks to yet another audio system, which is now implemented in C++. But this thing is called audio system, which talks to something called audio policy service, and it comes from a completely different library. So what's going on here? What's interesting here is that this BP audio policy service is actually another binder proxy that will enable us to jump from here into this other stub called BN, and then from there jump into this other audio policy service. So there's actually two IPC calls here happening. One is from here, right? From here to the audio service, that's an IPC call. And essentially from here to here. That's another IPC call. And so what then happens is this audio policy service goes to the, essentially, this lives inside of something called audio flinger, which is responsible, which is kind of like pulse audio on traditional Linux, which knows the state of the audio device. And this goes and loads a HAL component. That HAL component actually goes, depending on the device you're on my device, it loads this library called tinyALSA, which essentially knows how to communicate with the audio driver, which is implemented using the ALSA framework, which is the, I guess, Advanced Sound Linux Architecture, Linux Architecture Sound, whatever. Advanced Linux Sound Architecture, I think that's what it stands for. And essentially now we are, say, muting or changing the volume of the device. Now let's talk about why we need this media server. What's interesting about the media server? That's kind of part of this audio playback. So let's say and we'll explain this media server in the context of, say, playing back, say, an MP3 file. Say you want to write an application using a media player, and you have read the documentation about the media player, and you now want to use the media player to play back an MP3 file. What do? You usually first of all, instantiate this media player object, and then you have essentially a bunch of methods you're supposed to invoke on it for proper playback. First, you need to set the data source of the data you want to play. Then you need to prepare the media player to put it in this prepared state, and then you can fire the start event where you actually start the playback. So what happens when you do all these things? Well, in the case of the set data source, the way you're setting the data source is you're passing essentially a file descriptor into the media player. What the media player does, it actually does the jump to the C++ version of itself via JNI on the client side, not on the service side. It then goes and it talks to something called the media player over here inside of the lib media, which actually uses a media player service, this BP media player service, to talk to a BN media player service, which is essentially a stub inside of the media server that answers to that call. But here's what's interesting. That original file descriptor that you gave to the media player gets transferred across the process boundaries through binder, gets duped essentially inside of the media server so that you avoid sending the data, the raw data to media. You instead send essentially a reference to an OS resource, which is essentially this file descriptor. And now you're essentially talking from this stub into the media player service, which then verifies what sort of media you're trying to play, and then finds the appropriate player. Now, why are there different players? Well, because your media doesn't have to be local. You don't have to send a file descriptor. Your media could have been, in fact, say, coming from the web. Maybe you're streaming the media, right? In which case, you're going to get a different player. You now say, okay, now that I set the data source, now I want to prepare the player. In that case, what happens, you're still executing the media player, you're still going into this, you're now going into the media player, and that's going and talking to this media player, which is then talking to this stage fright player. Let's assume it's stage fright. What happens next? Well, when you're preparing the media, what that means is you want to set up this pipeline through which you can play back this say, audio. Let's say an MP3 file. So how does Android handle this? Actually, Android tries to abstract this playback and split it into this kind of pipeline, very similar to some of you may know that the GStreamer does on standard Linux. Essentially, it's a pipeline of the different components that are involved in the playback. At the end of the pipeline, we have a component that's responsible for reading a single block of data or buffer of data from the file. Then we have another stage of the pipeline goes and decodes that or extracts essentially that block of data and extracts a particular stream from the block of data. Let's say it's an MP3 stream. Then another component in that pipeline goes and decodes that MP3 essentially block of data into a unencoded waveform, a PCM essentially wave data. And now we have something to play. So during that preparation stage, you're essentially setting up that pipeline. The interesting part of that pipeline is that basically the interesting part is the stage fright. Stage fright is a framework in Android that enables OEMs like Intels and Qualcomms and Texas Instruments and whatnot, Samsungs of the world, to go and implement a hardware optimized decoders and also encoders for the playback, right? Decoding and encoding of the different media files, right? So they provide these plugins in form of something called Kronos IL or OpenMX IL based APIs. And so what StageFright does, it wraps those plugins and essentially uses those plugins at runtime to decode this media playback. This is why the media playback tends to be device specific and why something works well on one device and not on the other, and why the battery utilization on one device when playing back, say, your H.264 encoded video is going to be, going to suck up a lot of battery or not suck up a lot of battery because there's different optimizations that OEMs put in these essentially plugins. So finally, you're now ready to play the media. At that point, what you're doing is you're again going into this media player, back into this, going into something called Awesome Player, which is actually responsible for the actual playback, which holds a reference to this pipeline, and then you're going into something called Audio Flinger. Audio Flinger actually does the playback. Audio Flinger has a thread or a bunch of threads that essentially do pull from this pipeline and pull packets of audio that they want to play back. And as they're pulling it, the packet gets read from this file, gets decoded, gets converted into a PCM stream, and now given to essentially the Audio Flinger. At that point, Audio Flinger essentially wants to play it. What it does, at least in my phone, is that it goes to an audio HAL, which is implemented in this driver, or sorry, I should say this library, which in my phone uses, again, the tiny ALSA, essentially, library to talk to this PCM-based ALSA driver that does the actual playback. The Audio Flinger can do the actual mixing of the different audio right inside of its own thread. Of course, it's also possible for that to happen inside of the driver itself. So you can see this is rather complicated, but the reason why they built it like this is because, again, they want the StageFright to be this kind of more open-ended framework that OEMs can add additional value into this chain. Of course, if you wanted to play this with lower latency to avoid all these multiple stages, you could have just taken a bunch of raw data, PCM data, created an audio track, and directly gone from there into the audio flinger and then down into this. And then you would avoid it having to essentially go to this pipeline. But then you are passing the raw data from your application to this audio flinger, and yes, you are copying this data essentially through the binder. Okay. Audio flinger also gets used to recording data, so this goes both ways. Telephony. Let's mention a few more, and then we'll be wrapping up and give you guys a chance to ask some questions. So what's interesting about the telephony, in case, let's say, how the phone application works, is that the system server doesn't play a key role here. Instead, when we actually want to send an SMS message or, say, dial a number, which is a more common case, is that we actually talk to something called RealD. RealD is a radio interface link daemon that loads a library called Rail, essentially, or this libsec Rail, which essentially is provided by your vendor. In case of my phone, I have an Intel-based modem, so that's provided by Intel, even though it's a Samsung phone. And so what's going on is that this basically, when I initiate that call, that goes through an internal, I want to spare you the details, it essentially goes through an internal chain until it gets this real sender. From the real sender, we're actually passing a message to a socket, which is a Unix socket, not a binder. And from the Unix socket, that message gets read by the RealD. The RealD then translates that message into a call into essentially this librail, which then goes into the particular library that my OEM provided to me. And then, so it goes this way, and then on my device, it uses a particular serial device to initiate that call. What's interesting here is that this also works the other way around. Say a call comes in, so it's an unsolicited request. Then in that case, that call gets read by Rail, the message gets deposited into the Unix socket. In this case, there's a Rail receiver that essentially initiates the call all the way up to me, and now I give an opportunity to answer that call. So so telephony is obviously a little bit special. It doesn't, most of the logic is in the phone application, which is persistent. And that's why it can afford to talk Unix sockets. It doesn't have to worry about ever being shut down by the system with the low memory killer because it's marked as persistent, and essentially knows that these Unix sockets are going to remain open and it'll be ready to answer the call when it comes in. Let's talk about just two more things and I'll be wrapping up. One is the device policy on Android. What's interesting here is essentially how, let's actually backtrack a little bit. How many of you have used the device policy or device admin APIs before? No? Nobody? Wow. So Android Froyo added support for this device admin APIs that essentially enterprise developers like to use to get more control over the device itself in their enterprise apps. What sort of control? Basically, an enterprise application that is granted device admin capabilities could wipe your device, lock your device, change the password on your device, change the password rules on your device, request that you encrypt your device, disable camera on your device, and a few other things. Okay? Quite a bit of control. Why would a developer, a user in their sane mind grant these permissions to an application that wants to be able to say wipe the device? Well, because basically, if they want to bring their own device to work and they want to get access to the enterprise app that gets access to enterprise data, the IT administrator says, you want to access this data on your personal device, you need to give us some control over your device. And so that's essentially the exchange. I give you control over my device, I get to essentially continue to use my device as opposed to have to use, say, BlackBerry or some other device that I may know or like. No offense to BlackBerry. But basically that's the idea. So, but here's the one interesting thing. Why would an enterprise application need to wipe the entire device? Right? That seems a little kind of like an overkill. Like you, sorry? Well, right, if it's stolen, right? And that's the idea. I mean, so basically, if the device gets reported as lost or stolen, or the developer or the user is found to somehow have breached the trust of the enterprise, they may want to issue a command that will wipe the device. But the question is, why would they wipe the entire device? After all, it's a personal device. Why wouldn't they just wipe the enterprise data? And the issue is, with the flash file system or the flash memory. It's extremely hard to actually delete data on a flash partition. You can try to delete it, you unlink a file, but all you did is you mark the data as unused anymore. It doesn't mean the data is not there, it just means you freed up the inode to that data, right? Well, you can try to overwrite the data, but because of the way flash works, you can't actually overwrite data on a flash partition. Because when you try to do that, your writes may actually be directed to a completely different memory cell on the flash medium. Why? Well, because flash essentially memory, comes with these controllers that do what's called wear leveling. They try to distribute the writes across the medium in order to wear it down evenly, because these memory cells have limited number of writes. They may be as low as 10,000, after which they start to essentially lose data. And so when you try to write over a particular partition, you may be essentially thinking you're overwriting a file, you may be overwriting something completely different. So what we need essentially a full wipe. So how does the full wipe work? So let's say we did initiate that full wipe. Our application wants to do exactly that. So we talk to Device Policy Manager. Device Policy Manager we get as a system service, again, exactly the same way as we've seen already. That talks to this proxy. Proxy talks to the driver, or the binder driver. That goes over here into, Device Policy Stub, which is actually extended by Device Policy Manager service. This will first check for whether the application has the privilege to initiate the wipe. Assuming that it does, it will then essentially talk to the recovery system, and from the recovery system, it will ask the recovery system, hey, I want you to initiate a wipe by rebooting the phone in the recovery mode and adding a special command to wipe the device. How does that happen? The recovery system actually goes and writes to a particular file on the cache partition, this file called cache recovery command, a command that says --wipe. Then and also adds a little bit of a little flag in the flash memory that the bootloader checks for to know whether to boot in a standard Android ROM or into the recovery ROM. Assuming this is all works as correctly as it's supposed to, the recovery system then ends up talking to the power manager to say, hey, I want to reboot the device. The power manager ends up talking to this power manager service. I keep forgetting which way it is. We can follow the arrows, which goes back, I believe, to the power, and this power is implemented by this JNI code, which initiates the actual reboot. Talks to the kernel and says reboot. So what's interesting now is that now the entire system reboots, right? There is no init, none of our services exist except for the kernel, and now the kernel basically gets loaded from this recovery partition, loads the recovery essentially binary. The recovery binary goes and essentially executes the command, or finds that they're supposed to wipe the device, and then initiates a low-level format of the entire data partition, because it's the only way you can ensure ensure is always a strong word. You can attempt to ensure that you actually deleted that data. Okay? So what's interesting here is that the service persists after the device actually gets rebooted. And let's see the last one, NFC. What's interesting here with this NFC, how NFC works, and in fact there was a session, I believe, earlier today, just actually before this one, on how to use NFC. But in terms of how it's implemented, what's interesting is that when you actually use this NFC adapter to say send an NFC message or subscribe to receive NFC messages, and you want to talk to the hardware, the way you're actually talking to the hardware, you're talking to a service that is over here. This NFC service is actually this NFC adapter service, I should say. That's what gets registered. And sorry, this is wrong. You shouldn't say policy service. This NFC adapter service basically looks kind of like what we've seen before. What's interesting is that this is not in a system server. This is not in the media server. This is in an application. The entire NFC stack is an app. The reason why this works is because this NFC this NFC app has been signed with essentially a platform key. It runs with an NFC user. It's marked as a persistent app, and it has special privileges to register itself with the service manager. Other apps cannot do this. Okay? And so at that point, basically when you're talking to it, you're still communicating over binder. The fact you're talking to something that's not in the system server You don't really know, nor do you care. And at that point, how the actual, the writing of the NFC data happens is, you talk, this is a little bit convoluted. You go this way, you go into the stub. From the stub, you go to the service. Then it goes back into this, into this, into this. It goes back into the service. Then essentially goes and loads an NFC HAL, which is, an NFC JNI. That goes to an NFC, libNFC, which talks to the actual HAL, which talks to the actual driver. Okay? It's not, the super easy thing to follow, but that's not even important at this point. I just want to kind of illustrate the fact that this actually exists as an app. So, and in fact, if any of you had a chance to see my brother's talk on remixing Android, this is how we advise, those of you that are building custom ROMs to add your own services. Don't actually add anything to system server. Add your services essentially as apps with these special privileges, have them essentially run with special users, make them persistent, and essentially you'll get the best of both worlds. You will not pollute the existing services, yet you will get essentially the same behavior from the point of end users, as essentially system services enjoy. Does this make sense? So that's basically it. I know there's a lot of other services we could talk about. There's more than 60 services on my Galaxy Nexus. This may vary from device to device. To actually find out which services you have and what's been registered with the service manager, you can just type ADV shell and type service space list, and you'll see a dump of those services and what they're called. And you'll kind of see what we're talking about here. This entire slide deck has already been posted at this URL. It's slightly newer than the one that you might have downloaded from the AnDevCon site. And the video from this very talk I will upload and post to the same URL. So that said, I think we have 3 minutes for questions. By the way, thank you guys. If any of you want to go, thank you for coming. I hope you enjoyed this. So any questions? Please.
How about the video phone? How is that going to affect the stats?
Video phone?
Yeah. So you can use the other.
How does a video phone work? Is that what you're asking? Well, first of all, there's no per se a video phone, but there is a camera, so first of all, there's a camera service. One thing I would recommend is go to Google for Android Builder Summit, which was a conference that happened just close to what was it, Redwood Shores in February of this year. And folks from a company called Aptina talked about the camera stack in Android. And so that will give you an idea how the camera stack works. Now, the playback of the video would essentially work in a similar way to how the audio playback worked. But you still need to capture the actual data. So, but it will be extremely important to understand how the actual video capture works.
How about the headphone manager?
Sorry?
The
Platform?
headphone.
Headphone?
Yeah. How is the stats?
I'm sorry, I have trouble hearing you. So you're saying a headphone manager?
Yeah. Headphone.
Oh, telephony manager? So you're talking about this?
Yeah.
How will it work with the camera? Unless there's an API that already makes it work with the camera, then unless you add it, it won't work with the camera. So if you wanted to add your own, essentially, alternative to this, when we talk about, so first of all, this telephony manager is about GSM or CDMA-like telephony, not IP-based telephony, right? What you're talking about essentially would be an IP-based, like a Skype call, right? That would go over IP. Now, there is already another service specifically for SIP and for VoIP. I don't know if there's something for video on top of that, and I don't know to what degree that is supported. But essentially, that would not be something you would bolt onto the telephony manager. You essentially would implement a whole new service. Okay? This is specifically for audio based on the GSM or CDMA spec, not for any sort of additional IP-based communication, whether it's voice or video. I think you were next.
Is it possible to restore data afterwards? Swipe data?
Is it possible to restore it? Well, the actual way the recovery system wipes the data is not super. It doesn't imply, it doesn't do multi-pass wipe. and so presumably, yes, it will be possible to restore the data. You know, you could. There are actually books on Android forensics. In fact, there was a talk on Android forensics at this conference that you could check out. But I'm sure there is. I'm sure it's possible. I don't know how easy it is. It's not available to us mortals, but there are tools that forensics folks can use. And by default. Now, I'm sure that if you are using a DoD-based device, they will have implemented that, so it does like some maybe explosive device. And in fact, there is a permission on Android called Brick, which is interesting to see how that's implemented. Anyways, you had a question.
I'm a little confused. I've gone to a few of these presentations now, and I've got an upcoming project where I'm going to basically need to run Android on a device that's definitely not a phone. And so some of these services don't make any sense.
Mm-hmm.
Now, in the very first day that I think there was a one-day session with
Karim?
Now, he was saying, yeah, you can add services all day, and he says when you start taking them out, things break. But from your discussion here, it seems like everything is so separate. I don't understand why you couldn't pull one out. It doesn't look like there's interdependence.
So first of all, okay, so you're asking how can you get rid of services, right?
Right.
Pretty much. So it's depending on the service. Some services are interdependent. So there's definitely dependencies between certain services. Like for example, the assisted GPS may use underneath the hood your network communication, or like the battery service may be used by notification service and whatnot. I mean, there are definitely some interdependencies. The reason why Android is not, first of all, built. So Google's primary objective was not to make Android be this super flexible, run on any embedded device you want platform. They specifically built it for the use cases they had in mind. So there are not a lot of easy to use hooks that allow you to disable these services. That said, what you can do is you can make these services, you can leave the services there, but you can actually change their operations, the invocations, these methods to behave like no-ops, or to return the nulls in the cases of, for example, for say Bluetooth. If the Bluetooth adapter doesn't exist, you simply return null. Doesn't mean that you yank out all references to Bluetooth from the device, because if you were to do that and somebody installs an app that expects those APIs to be there, they're essentially their code will not run, right? So you should then advertise your devices as not supporting different hardware using essentially what you can see from package manager how you would do that. But it doesn't mean that you simply yank out the code because of the fact that that's just not built that way. So that's why it's harder to remove it. It's easy to add. And you can see, in fact, for any of the optional services in Android, if you take a look at the source code, you will see how they deal with the situation where the physical hardware is not even present. And so how do they make it into a no-op? Okay. Any other question? Let's take one last question. I think we're done. Please.
Is there anything, can you give us any info on the historical reason why NFCs handle differently? And is it special or the whole bunch that way?
So why is NFC done the way it is? So first of all, the question of why is only something that I can guess. Google folks don't tend to actually put a lot of information as to why things are built the way they are in the documentation. I'm assuming that this would actually be a better way of building services than shoving everything into one giant thing, especially because NFC is not something that's expected to be supported on most devices. This way you can very easily not start the NFC service at all, and essentially doesn't mean that you yank out this NFC adapter, you just make it, you make it behave like, oh, there's nothing I can talk to. It returns null when you try to actually talk to a service. My assumption is that it probably has to do with that. So they just didn't want to have the NFC service exist on the side of the system server if most devices aren't even going to support it. Maybe there's some specific security implications. I know NFC runs with the NFC user identity, and maybe there's some specific reasons why it needs to do that. I haven't dug deep enough to understand that, but those are only my suspicions. I said one last question, so let's wrap up. If you do have additional questions, I'd be happy to talk to you as I'm leaving. But thank you guys again. Hope you learned something.